Here we have a pretty common application. We have R134A running through a compressor. It starts as a saturated vapor and it exits as a supposed superheated vapor, but we'll verify that in a minute. I'm going to go ahead and draw a schematic for what we're working with here. So we have a compressor and we have R134A entering it and R134A exiting it. Now I'll go ahead and write our givens. So essentially we have a saturated vapor entering, so we have X1 equals 1, so let me add that 1 into there. And then we have the pressure as 0.12 megapascals. We have 1 mass flow rate, and what comes in must be equal to what comes out, so M1 equals M2, which is going to be 0.108, and all of this can be equal to M dot. And then on the exit here, we have a pressure of 1.2 megapascals. Makes sense, so it's times 10 is the compression ratio, or pressure ratio, and the temperature at the exit is 70 degrees Celsius. Oh, as well as the the heat transfer exits at 0.32 kilowatts. So when you represent this in a number using the sign convention, just remember that it's going to be a negative number as it leaves the system. Now we can simply apply the energy balance expression over this system. So one thing to note, you don't have any velocities given to you and you don't have a difference in height given to you. So the energy balance equation is going to simplify into being 0 equals heat minus work, or power actually. This is going to be a rate, so heat transfer minus power, plus the mass flow rate of 1. So basically what comes in times the enthalpy at the inlet, minus what comes out, so M dot 2H2. Now, if we just plug in our numbers, we have 0 equals negative 0.32 kilowatts. Remember, kilojoules per second is just kilowatts. Minus W dot plus 0.108, the mass flow rate given to us. And we're just going to take that M dot outside of this expression up here, and we're going to have H1 minus H2. Now, the unit we're looking for is the power, or the variable is the power, and the unit's going to be in kilowatts. So we'll just move the W dot to the other side, and you'll have W dot is equal to negative 0.32 plus the mass flow rate, 0.108 times the difference in enthalpies. So all we need to do now is find H1 and H2. So basically at the inlet, so we have X1 and 0.12 megapascals. So at X1 equals 1 and P1 is equal to 0.12 megapascals, and you just times 10 it to get bar, so it's 1.2 bar. So at 1.2 bar in X1 we turn to table A11, so go to 1.2 bar and the saturated vapor Hg, and you see where these line up and you get 233.86. We go back here and we have H1 equals 233.86. And that's going to be in kilojoules per kilogram. Now we can very similarly apply this stuff at the exit. So we have at the exit, so we have T2 equals 70 degrees Celsius, and P2 is equal to 1.2 megapascals, or in other words, you times 10 to get bar, so 12 bar. So we go to 12 bar and 70 degrees Celsius. So at 12 bar, we have a 46 degree saturation temperature. We're way above that at 70, so we have to go to the superheated table for R134A. We turn to table A12. We go to 12 bar and 70 degrees, and we're looking at the enthalpy. So we'll see where these line up, and you get 298.96. Go back here. So you have H2 equals 298.96. Once again, kilojoules per kilogram. Now you just substitute all this back into our expression over here. So we have the power is equal to negative 0.32 plus the mass flow rate, 0.108 kilograms per second, times the difference of enthalpy, so what comes in minus what comes out, once again. So that's going to be 233.86 minus 298.96, and when you multiply the mass flow rate, kilograms per second, by kilojoules per kilogram, you're left with kilowatts. As the unit you have over here is also in kilowatts, you're going to be left with kilowatts for your power. Plug all this into a calculator, and you should get that the power W dot is equal to negative 7.0 0.35 kilowatts.